So welcome to this lecture about how neural dynamics architectures can be embodied. And I'll explain what that means in a moment. So let me start by first reminding of the basic principles so that we know what we connect to. So all we've been talking about so far has been about the dynamics of fields, how fields combine multiple inputs. For instance, in this example that I showed often, you would have some input that was already present before this plot starts. That's why we call it pre-shape, and some input that arrives just at this point that then drives the system here, in this case, through a detection instability to generate a suprathreshold peak. This would be one of those units of representation, a peak that's kept at a higher level than input by excitatory interaction and suppresses the field elsewhere, right? A stable state. So this is a transition from one stable state that's below threshold to a suprathreshold stable states, where something happens, a decision happens. We just previously last week talked about how these pre-shapes come about. And so these are stable states, and that will be very important in talking today about embodiment. Remind me, these instabilities are really what are the core mechanisms of DFT. I don't want to go back through that. Now, today I want to talk about how to drive neural dynamics by inputs that are not just functions we wrote down, but inputs that come from actual sensors. I'll use simple examples that we've used in robotics to illustrate the ideas and make it, and ultimately that connects back to the Braitenberg lectures where I characterized what a sensor is. And there's just one little point about what the intensity-like thing is that we'll have to talk about. And the more tricky or more elaborate part is about how to link to actual real motor systems. And it's in that context that we will have to confront two conceptual or theoretical problems. One has to do with normalization. The other has to do with coordinate systems, coordinate frames. So these will be the new topics in terms of methods and concepts. So let's begin with a link to sensors, which is sort of the easier topic. I'm referring here to work that I'm also showing part of that work sometimes in the summer semester when I'm talking about robots. So this was a neurally inspired robot, minimally, as you see, it's not inspired by animals in terms of its hardware. We built that in Marseille. Pierre Mallet was the engineer who built that, and Estelle Bichot did her PhD on driving low-level robots like this by dynamical fields in neurodynamics. So the robot is a vehicle, and the robot, mechanically, it's a platform that can rotate on the spot. So it has this 2 degrees of freedom, can achieve 3 configurations in space, position, and orientation. It has sensors for different purposes. There are some sonar sensors here that I'll not talk about. There's a little infrared device here that injects some light and measures the amount of reflected light for crude, uncalibrated distance sensing. That's important for obstacle avoidance. I'll not talk about that today. The sensors I'll talk about are these microphones, very cheap, simple microphones that we mounted here on the top that are supposed to give information about sound sources. So the example I've been talking about is phonotaxis, orienting to sound sources, so sort of like the Braitenberg example. The robot essentially consists of a computer here at the center of this setup, which was something ancient, like used to be called 386, I think, DOS driven. It's like out of a museum, you would now say. And so that computer simply numerically computed the solutions of dynamic fields, just like the simulators that we're using today. It didn't do that so efficiently. So it's actually the speed of this robot is somewhat determined by the rate at which it was able to update the field dynamics. And we had some electronics on the system to take the sensory inputs from the microphones ultimately as voltages that we obtained and feed those through some analog digital transformation as functions into the little numerical code that was solving the field equations. And the motor stuff that we'll be talking about in the second part was I'll explain how that works. And then ultimately from that, we derive mechanical or internal variables that have mechanical meaning, like the rate, the rate of rotation of every motor. And there were 2 engines that you can see down here, 2 electrical motors, very good high precision motors from Switzerland that were expensive for us then, who had very little money. That's how we drove the wheels, and them being very good servo controls meant that this vehicle was pretty much doing what we were designing it to do, that is rotating in the correct way and advancing the correct way. So I'll talk about not really the hardware, but you know, at a level where the rest that is needed for the hardware is really just very simple engineering, nothing really in terms of complicated signal processing or anything like that. And so the conception of how the microphones were used was based on a very simple characterization of the microphones. So the microphone sensitivity was assessed by how much a physical sound that is in a certain spatial location relative to the microphone drives the response of the microphone, measured by the voltage that you can take off on its output. You know, these microphones, of course, have some electronics that we just take as a black box, and that generates this response. So this is what we call the sensitivity cone of these microphones that we modeled as a Gaussian, and the 5 different microphones mounted on the vehicle would create 5 different sensitivity cones as a function of the orientation, you know, the orientation of the sound source relative to these microphones. And so you're familiar with these cones. Usually they're not shown as Gaussians, but as 2-dimensional sensitivity maps, which also where the angular sensitivity also depends on the distance, and we didn't take that into account. They have to do with the physical properties of these microphones. A lot of modern microphones, like the one I'm using, have very broad characteristic, which is sort of desirable, so that it can actually pick up my voice independent of exactly where the microphone is. Other microphones are more directionally sensitive for certain purposes. Those were directionally sensitive, had a cone where they were most sensitive to sounds that were within about plus minus 30 degrees, sort of like a 60-degree angular cone, caused by the mechanical properties, which was on purpose for us, because that meant that if there's a sound source in front of the vehicle, then only those microphones will react strongly to it that are somewhat pointing in the direction of that sound source. Here's an example. Let's say if over heading in the let's think of the robot for now as fixed, doesn't move. We've disconnected the wheels, or we put it up on a support so it doesn't turn, and so it doesn't matter. Heading direction and angle on the vehicle are the same. So in that sense, these microphones are pointing in the direction of space, or you could also think in the direction relative to the body of the vehicle. And so if there are sound sources, like for instance, in these directions that I marked here by these lines, then the microphones will respond to these sound sources in different ways, depending on how close in angle they are to the sound source. So for instance, those microphones that are pointing sort of to the side don't react much. Those that point in the direction of these sound sources react more strongly. And of course, the other thing is the amplitude of that response, and that is the sensitivity of these microphones to loudness, which we didn't model because we were not interested in representing the loudness. We were just interested, we just used it as an intensity variable. So there was a monotonic dependence that would actually saturate, by the way, a monotonic dependence of the voltage returned on the sound level. These microphones actually also had some frequency specificity. They liked relatively high pitch, for instance, female voices, more so, and violin. You will see we use violin music versus the lower registers. And actually, it's well known that good microphones are better quality microphones are required to capture low frequency voices frequencies. But we're not interested in that, so we're just taking that as something empirical variable. So we're taking the raw response, and so you see here, for instance, this sound source was louder than that sound source. That's why these two microphones that are pointing this direction respond more than these microphones. And so what we do as a sensor interface is simply take the intensity to rate code transformation. The physical device, the microphone and its electronics, is of a model of a sensor that transforms a physical intensity into a rate code. That, if you think back of the Braitenberg lecture, that characterization is now done in hardware, so that we take from each microphone that rate, which is here just a real number, this positive number, the level of activation we get from the microphone, take that as input to the field, as an right-hand side of the equation of motion. So that's an input that's positive, and that that's calibrated by 0, meaning very low intensity in terms of what we set up in the experimental setting, and we don't have a real scale. We don't care about that scale, so we just make sure that when the microphone is, when the sound source is as loud and as close to the microphone as we care to examine, that then we get a good amplitude signal that induces a peak. That fixes the scale. So from then on, we're doing field theory stuff, dynamic field theory stuff, in the sense now we're talking about space code, that is about different microphones representing different things, that is different orientations, and that's fixed, namely fixed by the microphone being mounted a particular direction on the vehicle. I'll come to the coordinate frames again at the end of the lecture. And so different microphones contribute here to different regions here in the field. So every microphone provides input to the region of the field that matches its heading direction and it provides input as described by a forward kernel that reflects that Gaussian. That is, we're taking that Gaussian to distribute a single number, the intensity from that microphone, to a region of the field. It's a Gaussian. So for instance, the inputs that you use in the interactive simulators have these sliders. You could think of every slider as being a microphone, and that the intensity sensed by that microphone determines the slider setting, and that then determines how a Gaussian is being put into the field. As simple as that. So there are only 5 sensor data, 5 intensities from 5 microphones that are time courses, of course. And those provide input to the field, as simple as that. So with that very simple picture, you can then very directly do experiments on this vehicle to tune the field to do the right thing, that is to have the right instabilities that make meaningful states. So here's, for instance, how we set up this field to do detection. So this is, again, the robot fixed in space. We have a sound source, which is simply a loudspeaker. You'll see it later, through which we were playing Vivaldi. We always played the same piece. Vivaldi is somewhat high pitched and it varies. It's like the 4 seasons. And that makes that the sound source is fluctuating a little bit. And that is important. For instance, we'll look at working memory, we'll look at stabilization, and that's important. So you see here, for instance, I should say there's a time course of that input here because we changed the volume of Vivaldi by just turning the knob on the amplifier by hand, like Marseille cheap style experiments we did. We tried to do it at a constant rate, but it's just by hand. And so what you see here is the input to the field, that is the superposition of the 5 Gaussians to the field when we slowly increased the knob. You see, initially it was below threshold. We didn't, so the field, this is the raw input, so we probably just didn't create significant sound. And then it starts here. I wonder if these here at the end, maybe there was some mechanical perturbation here, I don't know. And as you see, there's more input that is picked up initially probably just by a few microphones, and it's probably the inner 3 microphones that contribute here, somewhat fluctuating because the music is fluctuating. And this provides input to the field, and you see that there's a little bubble here, and about here, the detection instability is encountered. You see the peak grows out of it in some continuous form. It's an instability, but you go through it in time. The field needs to integrate that transient going to the new state. And also the amplitude of the peak is somewhat dependent on the input amplitude, as you saw in your own simulations. And you see most clearly that it's a self-stabilized peak because of the inhibition. You see here on the side how the field goes below resting level as the peak forms by inhibitory interaction. So this would be a suprathreshold peak. If we apply the sigma to it, that would return something positive, and then we will drive the vehicle motion from this peak. So here is a property of this. This is a field that can make selection decisions. We put up two loudspeakers and played music through the two loudspeakers. It was actually the same music played. It's a stereo. Oh, stereo loudspeakers. It's not exactly the same music. No, sorry. You know, it wasn't calibrated perfectly. So you see, the one was a little broader, perhaps, but less intense than the other, fluctuating in time. And as you see, the field makes a selection decision, selects the rightmost, and then stabilizes that selection and suppresses the other section. So you see stabilization of the selection decision. You saw here earlier, it's also stabilizing, right? So you see the fluctuation of the input, and this is less fluctuating. It's suppressing that fluctuation because of the stable state. The selection capacity creates actually something that engineers call robust estimation, which means that we're suppressing outliers. And this came about here in the example in that we had a single sound source, but we put some cardboard on the other side. So there's reflection of the sound, some echo, which drives the other microphones here also somewhat, so that there is this broader band. And where the peak simply has the property of sitting on the local maximum. That's the mathematical solution if you look through the Amari equation. That's what's happening. And so it, in effect, suppresses these outliers. If you just took the mean of that, take the input as a distribution and compute its mean by normalizing, then you would get something that's biased here toward these outliers, and the field suppresses that. So this is actually a very useful property of the fields that one could link to probabilistic thinking of such neural processing. These are decisions, so you select and detect, but then they stay connected to the input. And here you can see this concretely. What we did is simply take the loudspeaker and move it somewhat continuously in front of the vehicle, move here from left to right. So the input shifts, and the peak tracks that input. The peak is locked by input onto the stable state. You had a chance in, I think, the last exercise sheet to play with that yourself, to move a peak along by dragging the input along. We did this in this memory context in the last exercise. And you see that the field tracks this. This is not just a slow drift, because the input is an input driven. It's a self-stabilized, not a sustained, self-stabilized peak. So it only exists while there's input present, and then it gets dragged along. There is some delay. The peak doesn't follow this instantaneously, and that's the usual delay you have in estimation. And finally, we could operate this also in the sustained regime. So here is the sound source was turned off after a short moment in time. And so this is the peak driven by the sound source. And this thing here, that is the sustained peak here at the end. In this particular demo, we actually turned the self-stabilized peak off. So, you know, sort of like in the robotic context, it doesn't make sense to memorize a sound source for a long time, because as you drive around, the heading direction in which that sound source was first detected changes. You move relative to that source. So it doesn't make sense to keep the direction in memory for too long. It's not sufficiently invariant. So we had some special mechanics where we picked up, detected with a field detector that will come in the news year. We'll talk about things like that. The peak detected, there was a peak here, sorry, here actually, this region, and no input. And when it detected that kind of situation, and detected really means there's a function that computes that, and that is then non-zero whenever that difference isn't zero. And when that function occurred, we had a simple dynamics of the heading, the resting level that with a constant negative input that would create a downward ramp and lower the resting levels, at which point to the reverse detection stability. So we're losing the memory here after a fixed amount of time. So by making this ramp constant rate, we can fix the time it takes to reach the point where the memory peak is lost, and then the resting level was actually relaxing, had a linear dynamics to relax then back to the resting level. So some kind of period during which you have a harder time inducing a peak. It's sort of like inhibition that is being built up in the field. You can think of lowering the resting level as a form of inhibition. So we did this just for practical purposes, and the function of this form of working memory is really to stabilize the input against intermittent sound and music. Or we originally thought of this as a demonstration of humans talking to the robot, and even though the robot doesn't understand anything, it would just follow that voice, and the intervals in the voice would be where the working memory has to the working memory has to bridge. So it would be just very short term. That's why this would be fine. So here's an example of that vehicle going. I think you hear the sound as well, which comes out of this room here. So actually, you see it has detected the echo first, echo here off the wall. That's why it's driving here to the left. And that echo goes away at some point because of the angular conditions in which that echo would be perceived. And then the vehicle actually moves into the room, always tracking the sound source. And the speed with which the obstacle drives has to do with the integration, how fast we were able to solve the equation on the robot. And when you can't make the dynamics very fast because you have to numerically solve it in real time. And when you make it slow, then you have to move slowly so that the system has time to reach the attractor before the vehicle has moved a lot. There's also obstacle avoidance on this, which I don't explain. And so I'll go ahead and show that it actually does go to here's the loudspeaker. We also controlled the speed of the robot in a way that it would stop when the intensity was high enough. So I'm not explaining the obstacle avoidance, which we do talk about in summer semester. And I will be talking about the motor part now. So far, we just talked about how the sensory part of this. So that just says that. So let's talk about the motor side of this. The sensory side is somewhat straightforward. There is an interesting problem related on the sense side related to normalization that I gloss over here, where you could worry about. Let's say if you operate a robot like this in an environment where there is a lot of sound, versus there's not so much sound, then you might have a problem that you're not sensitive to the differences in sound, right? There could be a lot of ambient noise, or very similar with vision, right? You have a very bright room versus darker room, and you're just interested in contrast, and you know that in vision we're actually using things like contrast or relative background luminance. Remember, we talked about that. And there's a lot of know-how in the nervous system about that. You know that your nervous system is actually able to normalize locally, so that you're able to see contrast in bright spots like the window, and also contrast in dark spots like somewhere far from the window. A very large difference in physical intensity, and you're sensitive to that. And that's something that people study a lot, how that works, and it's all could be conceived of as terms of neural dynamics, actually. Recurrent connectivity that modulate the gain, the effective forward coupling strength. It's another topic I'm not going to go into. That's the only part where that link to sensory information has some intelligence, and it's an important part for practical purposes, how to make these systems robust under change of the sensory environment. And to do that, you have to do more at the front end. You already saw that the field itself does contribute to that, because a peak depends less on the input strength than the input strength itself. Essentially, you have to leverage that all the way down and do that at the appropriate levels. So I didn't want to go into that too deeply. It connects also just conventional neural network modeling that doesn't necessarily involve the instabilities. Now, on the motor side, we'll encounter more substantial problems. And so on the motor side, I just want to connect that to what you heard earlier in the course. What we're looking at is how this inner dynamics, which in this Braitenberg lecture, I just made these funny errors that the activation that goes along this cable could be passed across multiple neurons. And it could be self-excitation, things like that. And now we know, of course, much better how that's actually done. So what we have to do is to connect that to that motor dynamics, which in the Braitenberg vehicle, remember that was this kind of derivation we had where we showed that the way the Braitenberg vehicle is organized, it translates any distribution of intensity in the environment into a dynamics of the heading of the vehicle, where depending on the initial heading, the rate of turning of the vehicle on the spot depends on that in this characteristic way that has a zero crossing at the direction where intensity is locally maximal, and the slope of that curve is negative, and that makes it an attractor. And that's an attractor, a physical attractor in the, or we call that of the behavioral dynamics in the space where the physical state of the vehicle, the heading or relative orientation to the sound source is varied. And it's in that physical space where the turning to the sound source the system acquires the state that corresponds to this attractor. So we need to make the connection between this sort of thing that happens at the periphery, the behavioral dynamics, and the field. And you can already sort of guess it's got to be about somehow some peak-like thing creating attractors that is at the local maximum of the peak. Except here the peak is directly is a model of the environment. The environment makes the peak, and the two sensors, by sort of computing the difference, extract something about that, and that's how they erect this dynamics. And in a little while, it will be the fields that make the peak, and we'll have to think about over which space they are and what do we do if there's no peak. So I already hinted at that. Now, I didn't in the Braitenberg lecture really introduce the behavioral dynamics very much. And I teach about that quite extensively in summer semester. So here I thought I'd give you just a brief introduction, and then in the chapter 4, if you read it, there are boxes that review that part. And those who have heard the summer semester or are going to will learn much more about that later. For the purposes of this lecture, you don't need to go too deeply into that, especially not into the obstacle avoidance thing, which is introduces some new concepts. But of course, you're welcome to still look at it. So I'll take you briefly through the notion that we introduce what we call behavioral variables that capture the physical state of the system, and the time courses are generated from attractors enabling the system to actually move, to behave, and point out about something about tracking and bifurcations. So here for the vehicle, a simple way to describe the physical state is to describe the orientation of the robot relative to some fixed axis. This is what we call the heading direction, right? If you had like a magnetic compass on the vehicle, then you could read off the heading direction directly from that compass, like relative to north, right? Or if you had some landmark recognition, you would see some wall, you could say, well, the angle relative to that wall. It will turn out that for the behavioral dynamics to work that we'll look at later, you don't actually really have to know the heading, you only have to know differences in heading. Conceptually, it's still important to think of this as something that's fixed in the world. Differences in heading make direct sense. You can get, turn by giving different speeds to the left and right motor. You can compute how much, depending on how large the wheels are, how far they are from each other. And actually, these two are enough to determine how much difference in turning rate of the wheels leads to change of heading. And the change of heading is really what we'll be then using. But to understand why it works, we need to think of the heading direction in this way. That will be important again when we think about the level in which sensory information about the world should be represented. And it will also be in terms of heading rather than in terms of onboard variables, like where relative to the nose of the vehicle a sensor is mounted. So if you have a variable like that, you can express the task, or here the task of going to a particular direction as a particular value of that heading direction, right, of that variable. So for instance, here, if you want the vehicle to go to this target, what you want is that its heading direction, becomes that angle. If these two angles are the same, the vehicle is heading to the target. So very simple. You make it an attractor of a dynamical system. So I'll say in a moment how that works. So heading direction here is a good variable to describe the behavior. So when you look at an animal zone, you have to find the right variable to characterize its behavioral competences. As an engineer, you have to design a robot to do that. And in both cases, it's good to think about what kind of variables are good for that. So for instance, here, they are good in the sense you can describe the desired behavior, so desired in terms of the tasks that the system can solve. You know, in the case of an animal, you have to say, you know, the performed or the kinds of motor behaviors that we find these organisms bring about. And I say enactable, there are more precise concepts in engineering like controllable, reachable, and so on, which have more technical meaning. Enactable really just means that the variable is enough to then actually bring about that state. For those of you who studied some of my earlier work, which maybe nobody in this course, you know that I did some work on relative coordination where periodic processes are organized, and we talked about a variable being the relative phase. And that was an example of a behavioral variable that isn't actually really directly enactable, because just because you know the relative phase of two rhythms doesn't actually tell you how to bring about a particular value of that relative phase. And one had to go to a different level of description that we called the oscillator picture at the time to bring that about. So it's not an empty concept. It's not every variable that is enactable in this way. And then the variable is also good in that you can map different constraints on the vehicle as values or ranges of values. It also has so here, for instance, you know, the constraint according to the target just means that I can express the target, that constraint, as a desired value of the heading direction. And that has to do with the invariance of that. So the invariance is here expressed by the fact that this angle psi is the same no matter what the initial heading of the vehicle. So if the vehicle is initially heading, you know, a very different direction, it's always the same heading angle that is the target. See, this it would be hard to express on the vehicle. The only way to express it on a vehicle would be to say, well, I want the target to be at 0, to be, you know, my nose being headed to the target. That's all right, but that can actually only do one target, right? If you have multiple targets, then it's only true because all of these targets are mapped onto the same thing, as namely it's got to be in front of me, and I can't actually talk about how these different constraints combine, for instance. And I'll see in a moment that we can do that for the dynamical version. So this is what I call the appropriate level of invariance here, invariant under the initial orientation of the vehicle. So the second step is to think about the dynamics. How does dynamics come about? In the Braitenberg case, I derived, you know, from these two sensors this particular dynamics, but how do I characterize that? And here the notion is that we're generating the time course by postulating the dynamical system, and the dynamical system is such that the desired behavior is an attractor. So moving to the target, that should be an attractor. And we'll have to take your sensory information and make that erect the attractor. That's what I'll be talking about. So here's very simple. Attractor really just means that when phi, the heading direction, I call that phi here, it's here on this axis, equals psi, the turning rate is 0. Turning rate is the derivative in time of the heading direction. So here it's 0 when phi equals that psi. And it's an attractor, that is, I have to have a negative slope. So if I have a slightly larger heading, I should have a negative turning rate and therefore, you know, move in here, and similarly on the other side. So you move into the attractor. So that function, if I can erect this function, the red function, as a function of the heading of the vehicle. If you turn the vehicle on the spot, how does the turning rate depend on the current heading? It should have a 0 crossing when it's heading right in the right direction, and have the correct sign so that it is attracted back to the correct heading, right? That makes a lot of sense. And so if you have sensor information, you would have to transform the sensor information into that. The Braitenberg vehicle does that in one particular way. So when you have that, then the system can integrate multiple constraints. I was hinting at that. So for instance, if you have two possible target sources of something, you can think of each of those targets erecting this kind of dynamics, this contribution in lila here, and their superposition, adding them would mean the superposition is the dynamics that actually acts as the red curve. That would, for instance, in this case, have an attractor. If it's everything is symmetric, they have the same intensity, then the attractor would be right in the middle, would be an averaging solution. The red is just the sum of the two lines. And that might make sense because these targets are close enough so that the vehicle can be on top of both. So maybe that's the right solution. And then you might have a case where that's no longer the case. The targets are sufficiently far from each other that you want to select one or the other. If you apply the same logic and the range, angular range of these contributions was done right, then when they are sufficiently far from each other, they don't affect each other anymore. That is, there is an attractor for the sum of these two contributions. That will be the red curve here. That's right on top of the individual attractor. So that will be erected just by the attraction function to this target. That's one of those, and or to the other target. That's the other one. So there are two of these curves that have attractors here, and now superposing these two leads to the same attractors emerging almost. Now, a slight shift. And in between there is a repeller, zero crossing with positive slope. That is the boundary. So depending on it's the boundary of the basin of attraction. So depending on your initial heading, if you're close in heading to one target, you're attracted to one. If you're close in heading to the other target, you are attracted to the other one. Very simple. That's where you see this coordinate frame is useful. It will be much harder to express that in terms of something that's defined on the body space, because both of these would lead to a single attractor, namely the one where the target is right in, where you're heading to the target. So the angle at which the target is in is zero. So in the Braitenberg case, we derived that from the sensory inputs. And now we have to derive the same thing from a field like that, right? And I will gloss over the fact that the behavioral, we discussed then that the behavior can make a decision. That is, if you have two peaks and you erect these two attractors from them, then it will be your initial heading that determines which you select. That's the selection decision, while the physical stimulus doesn't make the decision, right? Both of these peaks are still there. And in the neural field, of course, we will make the decision here at this level. I mean, we'll represent the intensity, and then in the representation, we can make one peak win and the other not. And then we don't actually need the behavioral system to make the selection decision. And maybe sometimes we could have both. Okay. Now, as we confront that, there's a lot of text on these slides which you can use later. We'll confront problem, and I'll talk about that problem. So what we really want is that the field creates the attractor. So the first thing is the field is defined over the same space as the dynamics that we have here. So we don't really have a problem. I'll come back to that in a moment. It's still some problem hidden in there. So the way we conceptualized it, that's okay. So all we need to do is translate a peak into an attractor that is localized exactly where the maximum of the peak is. So it's sort of like the Braitenberg thing, but that would be a very specific way of using two imaginary sensors or so. So as we're confronting that, as we're trying to find a general recipe, you point to a problem. You might think a simple thing would be to just somehow estimate where that peak is. The peak position is the correct thing. So we would have to read that out. And a very natural way to think about that is to think of the activation field as a probability density. That's actually formalized and done like that in so-called Bayesian approaches to estimation, which essentially postulate that the nervous system represents explicitly probability distributions. So the neural firing inside the brain would be representing a distribution, and then on readout you would have to estimate from the distribution its mean. And so the correct way to do that would be the theoretical mean that I have written down here. Fortunately, I just noticed again, I should have used a different letter here at the bottom, x prime perhaps. These are not the same x's on the top and the bottom of this ratio. A theoretical mean. Theoretical means that you have the distribution and you compute from the distribution the mean, as compared to a sample mean or empirical mean, where you just have example values. And for instance, the arithmetic mean is a way of having a lot of samples, and taking the arithmetic mean is a way to estimate the mean from samples. But if you have the distribution, then you can compute it theoretically. And so if you think of the sigmoid applied to the neural field as a probability density, then the theoretical mean would be just multiplying every the probability density with the corresponding value, here the heading direction, and summing or integrating over all the possible values. If the sigmoid was a real probability density, you would be done, but the sigmoid is actually not normalized. Now, probability densities have to have that property that the integral over all possible values, which is here at the bottom, has to be 1. Only if that's right, then you get the correct mean. That's why there's different letters in top and bottom, right? And so the theoretical mean with a non-normalized distribution needs to take this form, where this is the normalization factor here in the bottom. So that's a good thought about this. And when I say Bayesian estimation, I mean people who say the currency is probability distributions in the brain, those represented, and they are about how you combine multiple sources of estimation. So for instance, they say as a sensory system or perceptual system, you're never making a real estimate from scratch from just the sensory information. You always have some initial guess, which comes from your knowledge about the world, from so-called priors. And you can take those into account through essentially using the formula of conditional probabilities, sometimes called the Bayes formula. It's a very simple formula. And there are actually some experimental signatures that people use such things. So for instance, when you have to judge if a ball in a tennis court is inside the line or outside, and you make the sensory information really very difficult to use, for instance, noisy, or you get a very short piece of movie only, then people have a bias toward estimating it's just inside the line. And that is justifiable perhaps by the fact that if you watch a lot of tennis games, that's what most often happens, because many of these players are able to hit it right there. And so you would have an initial guess, sort of like in the gaze paradigm 2 lectures ago. Would have an initial guess that lies where the prior is. And so based on these kind of ideas, people have that thought that the way neural representations are read are by using probability densities that are neurally represented to read out the estimated value. There's a problem with that, and that's the problem I'm hinting at here, that normalization problem, that is, what if you have no peak because you have no sound source? If you were to take this approach, wire up the neural network to do that, that's called divisive normalization, by the way, and there are some models like that. Then you have to do something special so that you don't divide by 0, right? Probability densities are always normalized, but in the nervous system, you might sometimes just not have an estimate at all, and represent that by the absence of any suprathreshold activation. So that's a problem. So some people have argued, like for special mechanisms of how to deal with that. We have argued that this is actually never really the problem the nervous system needs to solve. It doesn't need to actually estimate the peak position. It just needs to erect a dynamic system that has an attractor at that position. And to do that, it doesn't need to do that this divisive normalization. Might have to do it somewhere else in the perceptual part, but not in the motor part of the system. And I'll explain that to you with a few formulas. So what we want is a system that when there's a peak, it erects an attractor just at the local maximum of the peak. When there's no peaks, no suprathreshold activation, what we then want is nothing, no contribution to the dynamics of whatever that dimension is about. The x in dimension is supposed to have the same dimension, be the same thing, right? This is the estimate of that. So a flat contribution. And the logic of that would be, well, for instance, if you have some initial value for your heading or for your x sitting here somewhere, then you're just going to stay put. Now, this is actually is just a situation where every value of x is a fixed point. It's not an attractor, because if you shift the system here, it doesn't return to the original value. It is a stable fixed point, though. It's stable in the sense if you are start in the vicinity of any point here, then you will stay in the vicinity. Without any other input, you will stay there forever. It's all fixed points, right? So you're staying close, but you're not being attracted. These things are called marginally stable attractors by physicists. Mathematicians, I don't think use that jargon. And you think the daily life example would be, you know, just a flat surface on which you can put, for instance, a ball. If it just has minimal amount of friction, you can just put it there and it would not fall off as long as the floor is really even. And any position is a possible position. So if you don't have any specific information about this dimension, that would be a fair thing to do. Just say, I'm not going to change whatever physical state I already have. That's a very good strategy, because if you have other sources of specification, for instance, you have some other sensory input, or you have some prior, some memory, and so on, those would add forces to this dynamics, maybe erecting attractor somewhere. And this is the best way to be neutral about that. So if you have other attractors and you have one contribution that is zero rate of change, then it's neutral. It doesn't change the dynamics, right? So that's a very good way to demand that the peak, no peak transition acts on the behavioral dynamics. And here I'm trying to show you that if you do that, then you don't have the normalization problem. So I'm doing, unfortunately, I switched here to G instead of sigma. Sorry about that. And so G is supposed to be the sigmoid. And what I have here as the first equation is the way that one could think of the field U erecting a peak at the peak position. You know, x dot equals, here's a minus, you know, minus x peak. That will be a linear function with a negative slope that has a zero crossing at x peak, at the peak location. I've put here in front of that function a integral. Now this is over x prime, so this whole thing is just one number, and that integral, that is the total suprathreshold activity in the field. So if there's a peak there, then that is the area under the peak, the activation in that peak. If there's no peak there, so the sigmoid G of U returns zero everywhere, then that's just zero. So this ansatz, if you wish, creates a situation like that. With a peak, you have a negative slope. The slope is the area under the positive part of the peak, right? So this area here would be determining the slope. You could put some extra coefficient to rescale that slope, but it would be proportional to that area. And so if it's zero, like here, then you have a flat slope. Now, that's what this equation does. Now, what I want to show in these two little maneuvers is that when you then insert the estimate of the peak from the mean, the theoretical mean, that the divisive normalization goes away. So let's do that, you know, inject this term. So here I use different letters correctly. So sigma or G of U of x times x integrated over x, and here's a different variable x prime. That's just the total area under the peak. And so if I insert that here into this term, I get I also have two contributions. I have the x times this here, that's here in front, and I have, you know, the same thing here times the x peak, which is here, this whole expression. And I changed again the letters to make sure that these are different x's here. So this is an integral over one x, this is an integral over another x, and that's a third different kind of x. And so now you see immediately that these two are the same, right? They're the same integral. And so they cancel. So what you have left is only this integral here. And so the only difference between this integral and that integral is that this is the x that we're talking about here on the outer x, while here this is the x that we're integrating over. It's called x prime, but it will be sort of like putting a prime here. So if I put these two under the same integral, again renaming the variable, then I would have one x that's the x outside minus one x that's inside. You know, I have this minus here, so this x here comes from that, and this one is a plus, and that comes from minus times minus. Now that's the plus. And so this expression now makes a lot of sense. That expression has no divisive normalization. It's equivalent to this one. And here what you see, what every location in the field does is it is a factor, the slope in front of a dynamics, a negative linear function of x that has its zero crossing at x prime, at that location we're talking about. And the slope of that negative function is the amount of activation that neuron has. So every location in the field votes not for a value, but for an attractor, you could say. It doesn't have to be exactly this very simple attractor. It could be an attractor where that's more like a forcelet that I showed, where it's not a linear function where you sort of multiply it with a Gaussian so it would fall off. And that's what we also often use in these models. And that doesn't change qualitatively the picture. It's just mathematically, they're not as simple to relate these two to each other. It has the same function effect. And that's what is at the core of the models and what happens in the robot that I just talked about. So the peak is translated to this in the same way. So that's the solution to problem number one, a very general solution. Problem number two, I just state, I'm not going to make a particular neural solution. That comes later in the lecture course. Problem number two is that both for the dynamical system and for the representation, we're using these world coordinates. For the robot vehicle, I've argued earlier that it's important that this is in this heading direction, and that's about the argument that we had in the summer semester. Some of you might have participated that. Then we went through that in some detail, right? I think it's in the summer semester, yes. It's the fact that the dynamical system as such has to be invariant under the initial position of the robot. So if you were to try to write down a dynamical system for the robot moving in terms of robot-centered variables, where you take the deviation from 0 as the behavior variable, so then the state would always be 0 because the robot is always heading wherever its nose is pointing. But you could add little forces on the other sides. What would be happening then is that as the robot turns, the dynamics change. And because the different contributions change, right? The sources would move relatively on your body, in your body reference frame. And that just means that this is not actually a dynamic system because the rate of change isn't determined by your state. It actually changes if your state changes. So the dynamics is only meaningful if you do that in the correct frame, in the frame where the dynamics is invariant under change of coordinates of its dynamical variable. This is something that is actually not trivial. People in the robotics lab course sometimes do this wrong. My students sometimes, when they build robots like that, sometimes get it wrong. When you have a robot that, without you wanting to rotate on the spot, that's likely you made a mistake like that, because that's what often happens when one doesn't do this right. There is a similar problem on the perceptual side, why this has to be in the world frame. That's easier to understand. In the world frame is where that information might be somewhat invariant, right? If you memorize where a target is relative to north, then as you turn around, that is invariant. If you were to memorize where it is on your body and you turn around, then it's wrong, right? If you say it was at 30 degrees and I turn, then I'm totally off, right? Because the world is invariant in its own reference frame, not in the frame on your body. And similarly, so that's if you want to really remember, like sustained activation, remember where a target was. Even if you just select, like you have two targets, you want to select the left one, with that, I'm anchoring my frame in these objects. I'm saying the left one of these two objects in the world. And so I'd have to carry that along. If it was in the body, then at some point the left one would be in that body location where the right one was, for instance, right? So yes, it has to be in a world frame. And so there's a problem in that the sensor information, on the motor side, we're saying it's not a problem because we're only interested in differences, rate of change, and they get rid of the point where the frame is anchored. In the sensor system, it's not as easy because you have the sensors mounted on the vehicle. So we call this your retinal coordinates. And so when the vehicle is at different locations, it would have to feed these inputs, for instance, from the 5 microphones to different locations in the world frame. And to know where to feed them, you have to know how the robot is oriented, or the organism is oriented relative to that world frame. You have to estimate your ego position. We call that the ego heading direction. You have to have an estimate of that. If you have a motor system, as I hinted, you could actually compute that by solving this equation here and solving, therefore estimating where your phi must be. That is called dead reckoning. Integrating your motor command has a long tradition in navigation. Excuse me. That's when you solve problems like that in vehicles, people call that path integrations, in other words for that. And what else? A couple of different terms: path integration, dead reckoning. Yeah, maybe those are the terms that are used for that. So that can be done. It is actually not a stable thing. That is, if you make an error, for instance, you have a slightly wrong estimate of your vehicle size, or your wheels slipped over the ground, and therefore, even though you gave this command to the wheels to turn that much, your actual turn in the world was a bit different. You're not going to recover that. It's nothing that resets that, and that's something that actually can be treated. There's a so-called SLAM, self-localization and map formation problem, which is about that, about using sensor information to recalibrate variables like that. But actually in the vehicle, it doesn't really matter that much, because as long as you occasionally get some sensor information that resets where you think an object is. So if you have the wrong estimate of your heading, then you're just going to transform that input to a wrong value, but then you're also going to translate it to a wrong heading direction command for your motors, and so the error cancels. So the error shouldn't change too fast in time. That's the only problem. So that's how the only case actually in this implementation where you really need to know the heading, because to generate the motor control, the behavior, you just need to know the rate of change of heading, which is the rate of change of speeds you send to the motors. But for making this transformation, you need to know the value of the heading, and that actually only shows up when you want to use something like working memory or so. So when you want to represent sensor information in a way that's not directly specified by the current sensor information. So that can be done neurally. What this is it's a neural map. So you can think of the input, if it's the field, you think of the field being represented by the input being represented by some sensory field. And what you need to do is map from one field to another field, one field over the retina, the other field over your body frame or the world frame and so on. And this is a special kind of map because how much the map itself, how much this input is shifted depends on a variable. We call that a steerable field. You can steer it. So in other words, you have to have cables or synaptic connections from any retinal coordinate to any world coordinate, and then you're activating a subset of those cables based on your current estimate of heading. We call that a steerable map. Not everyone uses that same term, and there's a lecture in the new year that I will be looking at that explains how neurons can do that. There are neurons in the brain that do things like that. They're called gain field neurons. So good evidence that they might be involved in something like that. So that is a problem that we know somewhat the solution of. And so in the robot that I'm showing you, this is actually done algorithmically. There's a little equation in there that determines the input to one location here based on this formula. And the neural solutions about how to do that. It's a funny case where you can write down a single line equation to solve that one. You need a lot of neurons to do this neurally, but then the neural system has a lot of advantages. For instance, can do calibration and self-calibration and so on. So I'll get that in the new year. So these together, that's what is in here. In here, we do the transformation in taking this microphone readings, which are on the robot, and put them into this heading frame. The heading frame is approximately aligned here somehow with the world. As the robot moves, this line might actually drift. So because it doesn't estimate its own orientation perfectly well, it might slowly get confused. But as long as this sound resets the peak in this frame, that's fine. So if we were to turn off the sound for a long time, then that would be a problem. But here you see the much more severe problem is that the direction to the sound source changes as the robot moves through the world. So it doesn't make sense to keep these memories forever anyway. And so in that sense, the problem with the world reference frame is not a severe one. And on the motor side, the peak is translated into this behavioral dynamics for the vehicle through the trick that I just showed you. And that steers the robot by just giving these two different, the turning rate is directly translated into a motor command to the two motors in a way that's not neural here. And that's how this whole system works. So you understand now how that works. I want to spend the last few minutes, I have another 20 minutes or so. First of all, I want to show you an embodied version of the A0B that I discussed last week. And that has an interesting history. And then in the end, I'll make a little comment how that is general. I mean, this is in the book, and this example it's these vehicles. You can think, well, maybe vehicles are maybe special. I can tell you that animal navigation is described that way, but then I'll make a hint at how this generalizes to, for instance, moving an arm. So we did a project which is not really published. There's a little bit in the book, and we have some other references to that, but we never got around to really publish that. It's maybe a task for the future. I actually even think of doing a little project where we do this again in some other form. So we put this robot onto the A0B model onto a robot. It was actually more meant as a pedagogical device to make a point. Esther Thielens, who did the behavioral work, was very interested in that. And in fact, we took our robot, the one I showed you, an earlier version of the one I showed you, from Marseille at the time to Indiana University in Bloomington. And it broke on the way. It was kind of hassle. And to demonstrate these ideas for psychologists to understand, if we actually discovered that we had made a mistake in an earlier version of the model, and I'll put a paper online that you can use to read up on this if you want, that explains that mistake, explains the error. It was an interesting story, but I'm not going to go too deep into that. So the vehicle we did was actually the one that I showed you that has microphones. In practice, it's a little shaky because of the environment and echoes and so on. So a later version used a smaller robot. The ones that we use in our lab classes, it was an earlier version, the so-called Capra version, that has a camera mounted. You will see in a moment. Takes visual input, and so that's the baby, the robot, and it gets the A0B task by seeing colored objects. There's just a little metal piece of metal that are painted in some way. So the color is the cue to which of in the visual environment where the object is. So it just orients to something that is green or whatever. I think we had yellow thing. So it orients to something yellow by just filtering out the yellow from its camera. It's a very simple form of segmentation based on color. And we organized the whole task by varying how large the object is in the camera plane. And that was done by moving stuff that we want to be large close to the robot. So for instance, the cue, when you tell the baby or the robot here to orient to one of those, the cue is just put close to the robot. We rigorously imposed the delay just by having a timer, so it wasn't done autonomously. And then after the delay, we push. So we made sure that it can turn here. So only after the delay it can turn, but it will only turn if there's a peak in its field. That's the more precise formulation. And so when we, at the end of the time we pushed both of these cue cards close to the robot, and that you will see in a moment induced a detection instability again and made the robot turn. So this is a case where the inputs are directly derived from the visual input. So visual input was, we're just interested in horizontal information. So along the vertical axis, we are just summing all the pixels, and we're doing this in different color channels, and you know, only the colors that are within a criterion of green or yellow count. So the more green pixels you have along the vertical, the more input. And so, for instance, this object that's closer vertically has more pixels in this, sorry, in this column, and therefore that will make a larger input than this object that's not as close. We had two scales. So we had one local scale where every pixel was sort of distributed according to a Gaussian to neighboring pixels. And then we had a larger scale where each pixel was distributed across the entire field. And that second input was to detect that everything is close. So the go signal, when like the box being pushed close to the robot. Here's an example of that actually working. So you see here, this is actually tuned to green. Here you see the segmentation, and you see in this illustration, you see what it recognizes as a green object.
I didn't find any matching places.
Oops, this is my phone thinking I said something to it. Let me restart that. So this is the A signal, turn it back, and now comes the go signal. Now the robot will turn. And if we go back to this again, you see here on the right, the red line is the specific input. So the red line is, you know, what the visual system extracts, how many pixels there are in the different directions along a heading direction. Or actually more precisely, this is the resting level. This is the input, I don't know what that color is, this rose color is the input, and from these narrow filters, and the red is the narrow plus the wide filter with the boost. And the blue line is the field itself. So I've seen here 0, negative, so inhibition here, and this is a suprathreshold peak, and the little dashed line here, that is actually the memorization that I will be mentioning in a moment. So it's let's say right away, it's a little contribution that reflects a memory trace of suprathreshold activation of the field. Here at the bottom, you see the dynamics of a heading direction of that is induced by this peak. So currently there's a negative slope because it's a suprathreshold peak, and the location is supposed to be where that peak is. I think it's just moving right now. The vehicle is just moving. We'll see that in a moment. You will see that the vehicle is rotating when this attractor arises. Let's maybe go through that. So it's here. So I'm pushing one of the, no, it's somewhere here. I'm pushing one of those closer. This is the right one. And so what happens is that therefore there is some input on the right. See, there's some input from the start because it does see the green slots even when they're far. And now this one is closer, getting larger. And the red line also, I think, is lifted up a little bit because this will provide some input to the whole field. And that induces an activation peak here. Oops. See, an activation field that doesn't actually become suprathreshold. So the robot doesn't turn because there is no suprathreshold peak. And then when it's shifted back, it actually decays. So it's back to 0, just pre-shaped. There's a little bit of a competitive advantage. See, the right peak is still a little bit more active because it takes some time to decay. And so after the delay, the two are pushed in. And now you see this whole thing goes up from 5 to 7, while the relative size of these two stays the same. And then the competition between these two peaks is decided, but just this little bit of bias where this is still a little bit more larger. And so at some point here, it becomes suprathreshold. You see, it goes through threshold, and this starts to, it was 0 flat, and now it starts to get a slope that's non-zero as the sigmoid, the larger the area under this, the steeper. And as this becomes steep, around the location where the peak is, then the system will be, so here's the 0 crossing. This is where the attractor is, and the attractor is where the peak is. This is where the state of the system is, and it will start to turn. See, it starts to turn at some criterion level. It does now, and you see here that the image shifts as the vehicle turns, goes to this attractor. Actually, in this movie, it doesn't reach quite the attractor, but ultimately he'll really reach the attractor and really position that on that. The movie ends before that, unfortunately. As the peak is generated, it actually lays down a memory trace array. You see the memory trace has formed even while it is turning in the world. So it memorizes that location. Yeah. So that's how that works, the embodied version of this. This is the actual experiment. So in actual, later it was yellow. There's music in the background because Evelina, who did this for a long time. She did this experiment like with the babies. See, now the robot was turning. This is one of those early training trials. Remember, I mentioned this last week. Excuse me. Sorry. So we were about here. See that here on the A trial, this is moved closer than the other. So this is one of those trials where the symmetry is broken early on. And I mentioned that the first 4 trials and a lot of these baby experiments are asymmetrical that way. And Evelina was actually here studying that this fact influences the outcome, that fact alone actually can explain some of the effects that are in the literature. So over time, she reduces that asymmetry. And so I think this is maybe, is it? Yeah, I think this is maybe where they're symmetrical. So let's again look at the start of the strategy. This putting in this large object is the specific cue. So she has cued the robot to the right side by putting that in. When she takes that away, this is now the delay. And after the delay, she just pushes these 2 objects close to the robot, now in a symmetrical situation, I hope. And now the robot makes the decision based on this little difference in activation. Actually, by the meantime, it has also more memory trace at A. That's how that bias comes about. Has more memory trace at A, so it's more likely to make a peak at A, which you see from the fact that now the robot actually is turning to orient toward that source. So this was an A response on an A trial. And I think the next trial might already be, now still another A trial. And then here's the B trial. So after 6 A trials now, the Q comes at B, at the B location. We move it, this is the delay, push it close, and the system turns to A. It's making the A not B mistake, and that's simply because it has a built-in memory trace at A. And it can repeat that. Okay, so that's a robotic demonstration of this. Heroic work, because we had to build the robot, will build the field model, tune the model to be right, and then actually do an experiment on the robot, which is like an experiment on a baby, except you don't need a lot of babies, but you need to repeat the experiment a couple of times because of some fluctuations that can happen. So we actually fitted experimental data in the robotic model. We fit it on in the sense, we tuned the parameters by hand. So you see here data that are of 3 very different natures. The blue data is from infants. It's experiments that were done in the Estothian lab over slightly different paradigms, 400 babies in different conditions. The cyan, light blue curve is the model, just use the model in simulation to account for these effects. And then the red, somewhat reddish line there, that's the robot in this kind of experiment, hand experiment. And you see, we get a lot of these things right. These are different probabilities you can compute from the data. For instance, here is the probability of making a correct response on B1 on the first B trial as a function of how many reaches there were to be on an A trial. Remember, these are the spontaneous errors. And what you see is the more times you go to B on an A trial, the higher the probability to be correct on the first B trial, so do not make the mistake. So this is evidence for that correlation that I pointed out last time. And this is this data that I showed last time for the model. So this is the probability to make a spontaneous error, that is to go to B on an A trial the first time, the probability of the first error. So as a function of when that occurs. So it's always about 0.1 or something, I don't remember the exact number. And the three are roughly right. And then this is the probability of making the error again as a function of when it first happened. So to repeat the error. And you see that that is a much higher number than that. And that was consistent with the model. And I showed you these two curves earlier, and the robot does that also. And you remember there was some dependence on the first couple of trials. The robot isn't quantitatively quite right here, but it's really hard to fit quantitatively the robot model. And then there are other things you can look at, error frequencies, so how many reaches there are to be, and how often you switch on A trials from correct to incorrect and so on. And these are things that we can capture by the model. So it's a lot of structure in this data that this model actually captures. So I mean, you don't need the robot to do this, right? The robot is in that sense just a proof that we've covered everything that's important about that. It also uncovers these coordinate frame issues and so on. Now, the last interesting use of the robot is in a way that you can step outside the paradigm with the robot. You know that in a lot of psychology, even worse in neuroscience, you study only very special kinds of behaviors and very special kind of situations. So in neuroscience, it's worse because you are not only restricted in kind of tasks animals will be doing, will be able to learn, reproducibly behaving, but also you're restricted by the kind of things that you want to do invasively, from the record from neurons and so on, what you can allow the animal to do. So a lot of animal neurophysiology was based on anesthetized animals or animals who are just fixed and just staring ahead, or they do very simple tasks that they have learned. It's a lot of effort to get them to do the task and then be able to record from them repeatedly. And in behavior experiments, you have a paradigm, and in that paradigm, you get reproducible behavior. That's what constrains your paradigm. You can't just take someone off the street and do something daily life-like. Too many factors, too many unaccounted for effects. And it's particularly true about baby experiments, where you're can't really give the babies instructions. You can only look at what kind of things the babies would sort of naturally do. And the A not B phenomenon is famous because it is one of those cases where you get somewhat reproducible, interesting behavior from a baby with manipulating the environment somewhat, but not too radically. And animal experiments often are a little bit like that. You can do instrumental conditioning to get them to do something, but actually not really anywhere as complex as sometimes discussed in the machine learning literature, where you learn, like through reinforcement learning, could theoretically learn very complex sequences, even though in practice it doesn't really work so well. And that actually often narrows the perspective, because you have this little island of knowledge where you look at one of those things and not at something else. We just had a group discussion about this morning in my own group, in the journal club of my group. So what a robotic model sometimes can do, it can account for data in this special paradigm, but you can also take it outside that paradigm and just have it behave, right? Because the robot is trained, you can describe its behavior. And so I'm going to show you some videos of this robot that throw a somewhat different light on the effects, sort of interpretation. So here are two movies. It's the setup where the robot is still going for a color. The target is actually not in the movie. It's here on the left of this arena. So that the camera, which is on top of these robots, you see here, the camera is here on top. can see over the border and see the object, and is heading for that object because that's the only object with that color in the scene. And we're using these little obstacles here to make the robot turn. It has obstacle avoidance, which I didn't explain, and it turns. It's actually not even so good. It just turns when it gets very close to the obstacle. And so what this contrast here illustrates is that the capacity to keep a working memory, to keep activation of in the absence of input stable, makes a behavioral difference. So the young robot that doesn't have that sustained activation loses the peak when it turns away. It's moving toward the target, but because it's turning away, it no longer sees the target. The camera has a somewhat narrow field of view. As it loses target, it has no peak and it goes straight. See, it just goes straight. And therefore, out of sight, out of mind, right? That will be what this demonstrates. While the old robot, and that means a robot where we tune the parameters of the field to be able to sustain the peak, what that robot does is as it turns away, it still has the peak, and that makes it turn back. It actually is able to do this for a second time. Here's this obstacle, make it turn away, it almost runs it over. And then it also turns back and goes correctly to the target. Yeah, so this is the point that people have been making, that this older robot is capable of, of keeping in mind the object, even when it's out of mind, here to turn back. Because the working memory isn't perfectly calibrated and all that, it really is important here that it can see again the target after it's turned back and can update its information about where that target is. But what I want to show you now is same thing. That on the right-hand side, you have actually, unfortunately, the video was stopped a little too early, but it reaches correctly the target location. This is the young robot, same as this, but it has the memory trace mechanism. Here it didn't have the memory trace mechanism. And so what happens when you do that is that that pretty much behaves like the old robot. No, not perfectly, but close. And why is that? Well, it is essentially, it has built a memory trace while it has that peak as a suprathreshold peak, and that memory trace stabilizes that peak. The memory trace, you think of that as something like a local resting level, so that's higher than the resting level elsewhere. That puts essentially slows the decay of the peak. You can even make that peaks at that location can be sustained because there is some localized input, that's the memory trace. And that's enough in this case to make the robot turn back after it was deviated. Here it's turning back, maybe not turning back as quickly as the older robot, but it turns back, and that makes it able to see again the target. And hopefully that would happen the second time too, which I don't know because the video ends here. And so why is that insightful? Well, it's actually very insightful because it just illustrates that the memory trace is actually a good thing. It stabilizes behavior. So if you have a hard time stabilizing behavior, memory trace helps. The NRB effect, in other words, is you see the young robot with the memory trace, that is the model of the behavior, because in the NRB effect, the memory trace is critical, right? If you don't have the memory trace, no NRB error. And I argued earlier, on A trials, the babies do act on something that is in memory, because the only reason why they go to A is because they previously went to A, except for the training trial issue. And so at least on the later A trials, that's what they do. And they do that because of the memory trace, right? And so the robot with the memory trace actually behaves in the same way in a task like this, where you lose the target from sight initially. So it's actually not about out of sight, out of mind, because it's not out of mind. The difference between the young and the old robot is essentially in flexibility. The young robot is specialized now after some training to this target. It will stabilize this target, but not any other target. So it's not able to switch to another target. Now, the old robot would also be able to now take on another target, forget about the old target, and stabilize the new target, because working memory is very flexible. subjective interference, which actually means that you can overwrite it, as we looked at last week. When you put a new peak, you can delete an old peak, update it. Well, the memory trace does this at least much more slowly and certainly not in an instantaneous decision. So so the robot model actually is able to uncover the functional significance of these different states. In fact, if you look back, it's kind of odd that for many years we said, these babies make this stupid perceptive error. Why do they do that? How stupid can one be? Why do they memorize something that's wrong? Well, because it stabilizes behavior. One can even think about why not use working memory from the very start. That is connected to this coordinate frame issue. That is, if you're not able to represent memory information in the appropriate invariant frame, then it's counterproductive. It would actually induce you to do something that's wrong. So for these infants, there is a coordinate frame issue because they're moving around the world. They're not very stable. And how do they remember where stuff is in the world? They have to be able to link the representation that they have of stuff in the world to where they currently are in the world. And this is something that's very likely to develop over this sort of same time scale as the perceptive error disappears, as infants start to navigate and start to be more able to link experiences from different places in space. And so it's likely that before they do that, they are not so able to extract invariants out of this sensory information. And that it might be therefore adaptive that they then don't operate their fields in a regime where they have sustained memory, sustained activation, because that would actually then be maybe misleading because they can't really have it in the right frame. While the memory trace, in a sense, is a lower level, you could think of that as being a conservative way of using working memory, where you don't make selection decisions at that level. But that part of the story we have never really written down. Maybe it would be useful to do that one time. This slide I should have shown earlier. This just shows that the robot model actually also does the thing that the babies do. That is, the older it is, the more delay it tolerates. But let's maybe close over that. So I want to close this lecture by just pointing out that it's not just vehicles that are like that. It is a generic property of the behavioral level of being sort of a dynamical system. And here I'm just alluding to stuff that is actually done in more detail in the summer semester. So physically, all actuators that we have when we generate behavior, right? Behavior really means you move something. Maybe it's just your tongue and you're articulated for speech, or your eyes, or you make very small movements, isometric force, and press on something and so on. But you do some physical action. And so that physical action itself, of course, is a dynamic system. As you know, every physical system is a dynamic system. Second order differential equation describes every mechanical system. These systems, mechanical systems, tend to be stable in the mathematical sense, but not asymptotically stable. They are only asymptotically stable if there's friction. But they have state. The state is the mechanical system. So there's already some element of that. And then the movement is brought about by muscles, right? The muscles generate the forces that make the movement. And these muscles, it turns out, are also dynamical systems. They have some inner state. So which comes from the physics or physiology of muscle force generation. So for instance, here's an example from a textbook of how the force that a muscle generates, and this is now the passive force, so without any control, depends on the current length of the muscle. So when you have muscles at different length, they generate different amounts of force given the same conditions otherwise. And this is the famous model for that, the so-called Hill model, that essentially says that muscles are like damped springs for some purposes. This actually creates some kind of attractor state that, although it's a attractor state in velocity space, so it's only transiently stable. There's a lot more to be said about that, but just saying the muscles also create some system, some dynamical system, and they already make a stable state. And then, of course, all muscles are controlled by reflexes. if you don't have these reflexes, you are severely handicapped. Deafferentation is sometimes being studied in the lab, and there are some unfortunate patients who have a motor disease that deafferents some part of their body, and they cannot do much. So in the summer semester, I explained that more carefully. The most important or most prevalent reflex that is around for every muscle, even the eye muscles which don't have a connection to the spinal cord, is effectively something like that. It's not in the same sense a monosynaptic reflex. So the scratch reflex illustrates that idea. So you have sensors in the muscle called spindles that fire when the muscle gets stretched, and that firing excites the motor neurons that contract the muscle, so that counteract that stretching. So they oppose stretching, and by varying the threshold of this neuron by some descending inputs, you can determine at which length that firing is turned off. They actually also inhibit muscles that work in the opposite direction, which I gloss over here. So that is a dynamic system. Actually, I had another slide. I thought, oh, maybe I didn't. Maybe I deleted that. It's a control system. There's a control system description. Here's a sort of a sketch of that. With a loop like that, you get a dynamic system that actually really rigorously has an attractor state. I must have deleted a slide that I actually made on purpose for this course. Very sorry about that. Yeah, and that makes actually that description that there's an attractor state out there. And that attractor state, that fact that the periphery is like that, actually really changes the nature of the movement system. So for instance, a lot of people think that when you generate movement, you must generate in their brain somehow the transient muscle activation. During movement, muscle will fire and then will stop firing, and then think of movement as being sort of sending out these bursts of activity that make the muscles move, which doesn't really look like an attractor. It really looks like neural activation has to be generated and generate some movement. But if you think through these reflex loops, then what you actually need to send to the motor neurons is not this curve. It is a curve that's monotonic, like that's just shifting the equilibrium position of that sort of equilibrium length. And then from that, this muscle activation pattern emerges. And I can't explain here exactly why that is. And then that actually means that you sort of like you go from one peak to another peak that can generate this kind of shift. And the periphery goes to the corresponding attractor. So in that sense, it's very, very general. Now, I haven't explained this in detail, and the movement system is more complex because it really matters exactly the shape, the temporal shape of how you make that transient does matter to overcome resistance and other things. But roughly speaking, it's still the same idea that in the periphery, you have attractors for a behavioral system, for a behavioral dynamical system, that is where physical things like muscle length and the joint angles and so on determine the state of the system. And therefore the demand on the representations in these populations of neurons that we have up there are not to compute some value, not even to compute some time course of values, but to set these attractors. So this picture can be used very generally. Okay, with that I close today's lecture, showing you how neurodynamics can be very trivially driven by sensory input, essentially taking just the rate code that comes out of the sensors and turn them into the rate as a level of input. And by taking different sensors into account, you can make the space code that makes the fields. And then when you have peaks in fields, you can project onto these peripheral systems with their attractors, erecting different attractors there. Again, the rate is essentially setting the attractor for every individual component, and the space code is which muscles you're activating under which conditions. That makes for different kinds of movements. And all of that, as I pointed out, coordinate systems are important. That is, these inner states in the nervous system are made invariant, more invariant than the sensor information and more invariant than the motor information. And they are just as invariant as the functional demand, the task demand, the environment imposes. So there is a certain kind of abstract. It's not just this little transition that we've earlier hinted at. There is some more complex circuitry really required to achieve this invariance, and then you can sustain activation or sustain decisions and generate meaningful behavior in the world. So some of that we will discuss in the second part, of course, in the new year. I will also really then be discussing how you get to even more abstractions. So this invariance will be the first and most elementary step, and then we'll show how you can do more invariant stuff until the high point of that will be that you do everything in your mind, that you don't actually do any sensory motor invariant. You close your eyes to imagine stuff, and then you can create cognitive processes with the same techniques that do something like mental inference, for instance. That will be pure cognition, and we'll get there. So with that, I close. And